Hello, hello. Let's do some optimization problems. So here we go. We're going to find the smallest perimeter and the dimensions for a rectangle with an area of 169. So let's let L represent the length and W represent the width. And we'll use some equations that we know and love from previous years of our education to analyze this problem and figure out what's going on. So here's the perimeter. We have twice the length plus twice the width, and then we have the area, which is the length times the width. What do we do with that? Well, we have some info already. We know that the area is 169. So we're going to plug that in, and we'll get that the length is equal to 169 divided by the width. You could have isolated for W if you want as well, but this is just the way that I went about it. So now we plug it into the perimeter equation, and we're going to get that P is equal to 2 times 169 divided by W plus 2W. And I transformed that W into a W inverse just for simplification purposes and to make the derivative easier using the power rule. So let's go ahead and take that first derivative, and we're going to get that P prime is equal to negative 2 times 169 times W to the negative 2 plus 2. All I did here was I did the derivative of 2W, which is 2, and the derivative of this, which we ignore the numbers, remember, and we bring down that negative 1, and then subtract the exponent of W by 1. So with this info, we'll set the first derivative equal to 0, and we'll solve for W in order to look for critical points, and hopefully that'll give us a maximum. So we set it equal to 0, and I move the 2 over to the right-hand side. Then we divide by this negative 2 times 169, and we get this fraction over here on the right-hand side on line 2. The 2's cancel out, and then I basically just flip both sides, and we get that W squared is equal to 169, not 169 squared, I apologize, because 169 is 13 squared, so when you take the square root of both sides, you get plus minus 13. So please ignore that too. That is a typo on my part. All right, moving on. We know that a width of negative 13 is kind of a nonsense answer given this situation, so we're only going to worry about the positive value 13. Now we take the second derivative, which is even easier. We know that the 2 just goes away, turns into 0, and then we do the power rule, bring down another negative 2, which makes the second derivative positive, and we subtract the exponent by 1 and get that negative 3. This gives us a critical point of, let's see, this will give us a critical inflection point at 0. I failed to do that calculation for you, I apologize. But it's really not a problem because we're only worried about positive values here. And even with an inflection point at 0, we're only worried about the points that are around 13. And if you think about plugging any positive number into this second derivative, you're going to get that it's concave up. So at this critical point, it's concave up. And we know that it's a minimum. So let's work with that and find our length. Plug everything in. We get that the length is 13. Then we plug 13 into the length and width, respectively. And we get that the perimeter overall is going to be 52, just from some very simple calculations. All right, let's do another problem. So we're planning to make an open rectangular box from a 9-inch by 17-inch piece of cardboard by cutting congruent squares from the corners, and we're going to fold up the sides. So what are the dimensions of the box of largest volume you could make this way, and what is its volume? Let's figure it out. So here's a picture for this problem. It's kind of hard to visualize in your head, and I would actually recommend you go get a piece of paper and try to cut out some congruent squares and get like an intuition for this problem. But the real takeaway here is that when you put down these congruent squares on top of, the piece of paper or the cardboard or whatever you're cutting the congruent squares from, you have the length side, and you're taking away an x on the bottom and an x on the top. So the length for this open rectangular box you're making is going to be L minus 2x. And then you have the width, and it's the same thing. You have a square over here of side length x and a square over here of side length x. So you're taking away 2x from the width. And then this is why I challenge you to, or suggest that you go get a piece of paper and try this out, because if you look at this for a moment, you can see that the x's are going to be your height for this box. And you can sort of see it from this diagram, but whatever way you need to do to figure it out. So using this information, we have that the volume is equal to the length times the width times the height, which we can set equal to and have W minus 2x times L minus 2x times x. We've still got a lot of variables going on, but given the statement of the problem, we can work this down to one variable and plug in 9 for the width and 17 for the length. And we get an equation in terms of x that we can find our max for. So let's take the first derivative. We get that the volume is equal to the thing that we set up in the last slide. So we take the derivative, and it might look like what I'm doing is a little magical, but it's really not. We did, I think, 2 or 3 problems in our previous breakout sessions, if you can remember, of taking the power rule, not the power rule, but the product rule of 3 arbitrary functions. And you basically just take the derivative term by term and then add them all up together. So that's what I'm doing, and I'm looking at x like f, and I'm looking at my 9 minus 2x like g, and I'm looking at my 17 minus 2x as h. So our first term, you take the derivative of x, leave all that alone. Second term, take the derivative of the 9 minus 2x, leave everything else alone. And then the third term, take the derivative of the 17 minus 2x, and leave these other two alone, and you get our full derivative. And if you take the time to expand it out, you get this nice little quadratic polynomial, 12x squared minus 104x plus 152. And we'll just plug it right into the quadratic formula and get our roots for the polynomial, which are also our critical points. So we have 2 values, but you will notice that if you plug in the bigger of the 2, you'll get a negative volume, which is kind of strange. So we're only going to worry about 13 over 3 minus the square root of 217 divided by 6. That's the only critical point that we care about. Okay, so here's our first derivative that I just restated. What we get from this is a much easier second derivative to take. You just do the power rule 3 times. And we'll get that v double prime is equal to 24x minus 104. So set that equal to 0, and you get that 13 over 3 is where we have a change in inflection, or a change in concavity, which is our inflection point. That's what I meant to say. My apologies. So what we only need to worry about is the concavity around our critical point, which is strictly less than 13 over 3. So all we need to do is check a really easy point that's less than 13 over 3, and then we know what the concavity is around our critical point, and then we can make our conclusion. So if we plug in a point before 13 over 3, I did 13 over 3 minus a half, easy peasy. You'll get yourself a negative value. So it's concave down, which means our critical point is a maximum. So we found it. Have fun, go plug that in for yourself and figure out what your values are. And if you ever have a box with those very specific dimensions, you will know exactly what to cut out. If you have some spare time, it might actually be fun to go get an 8.5 by 11 sheet of paper and work this out for yourself, and then actually cut out the squares and, go make the claim to a sibling or a parent or whatever that you have found the maximum volume possible. Okay, let's do something a little more number theoretical, a little less applied. So let's find a positive number for which the sum of it and its reciprocal is the smallest possible. So let's do our first and second derivative test on a function that adds a number with its reciprocal. We'll use the function s of x equals x plus 1 over x, which is what I just said out loud. And we're going to define it on the interval from 0 to infinity because that's all we care about, because they only asked us about positive numbers, not negative numbers or 0. So since s of x is x plus 1 over x, we take our derivative, our first derivative, and we get 1 minus 1 over x squared, and then s double prime of x, which is 2 over x cubed. Super simple derivatives to take using our power rules. So we get a critical point at 1 and no inflection points. This is one of those times where you really need to keep in mind that our domain is just 0 to infinity. Because if it was all real numbers, we would be looking at also 0 as a critical point and an inflection point. But no, not an inflection point, but a critical point. But we've restricted that, so no need to worry about it. All right, so no matter what we plug in on the domain 0 to infinity, the second derivative is always positive. So it's concave up, and we have a minimum at 1. And there you have it. Plug it in, there's your value. So that was a cute little problem. Let's do something a little more intense. So the reaction of the body to a dose of medicine can sometimes be represented by an equation of the form R equals m squared times c over 2 minus m over 3, where c is a positive constant and m is the amount of medicine absorbed in the blood. And then if the reaction is a change in blood pressure, R is measured in millimeters of mercury. If the reaction is a change in temperature, R is measured in degrees. It's a general equation. It does a lot of things. So what we want is we want to find the amount of medicine to which the body is the most sensitive to by finding the value of m that maximizes the derivative of dr dm. So let's take our derivatives. I've simplified R a little bit, simplified in, our purposes of taking derivatives. I distributed the m squared in there. And this should be a capital N squared. I apologize. So we take our first derivative and we get m times c minus m. I just did a little power rule magic. Then I factored a little bit. And keep in mind that this is the function that we want to maximize. We don't want to, or was it maximize or minimize? Yeah, this is the function we want to maximize. Not the function itself, its derivative. So we have 2 more derivatives to take, which are luckily very easy to take. So we get the second derivative, and if you notice, you can just do a really quick power rule stuff on this term, not the last term. We get the second derivative is c minus 2m, and then our third derivative is just negative 2. So that means that on the whole domain, no matter where we plug in, it is always, always, always concave down. So if we have a critical point, it's going to be a max. And we do have a critical point. It's setting this c minus 2m equal to 0. We solve for it, and we get that m equals c over 2. And it's going to have to be a max. Let's see. I think I talked this through in the last slide. Yeah, it's always concave down, so c over 2 is the max of the derivative function. And that's it. Those are the solutions to what you should have figured out by now are homework problems. So have fun with that, and have a nice day.